We will continue with our discussion of turbulent flow over a flat plate. In our previous video, we mentioned that the flow over a flat plate is made of different regions. There is a viscous sub-layer very close to the wall, where only the molecular mixing effects are dominant. There's no eddies we had to worry about. So we showed that in that region, the equation becomes a linear in the physical domain. If you plot in this regime, it's a linear curve. But in the logarithmic domain, it looks like a nonlinear curve. So this region is very close to the wall. It's called the Viscous Sub-layer. Then we said the next layer is called the buffer layer, where both the molecular diffusion effects and the eddy diffusion effects both are present. So the shear stress from the molecular effect plus the Reynolds stress from the eddy together will become a constant called shear stress at the wall. Then out here, the molecular stresses are very, very weak. So we are going to start looking at this region next. So this is the viscous sublayer. We talked about all of these. We came up with a linear equation. Then we non-dimensionalized it by introducing one new quantity called friction velocity. Then U over U tau was called a U plus, which is a non-dimensional velocity. This combination is also non-dimensional. It's called Y plus. Why do we do non-dimensionally everything? Then everything becomes universal. So if you plot this velocity dimensionally, depending on the tunnel you tested, this may be 100 meter per second or it may be 10 meter per second. This may be 5 millimeter or maybe 5.5 millimeter. So dimensionally, it's very hard to match one experiment to the other. But if you do non-dimensionally, you get a nice non-dimensional grouping. So indeed, if you go to the next slide, everyone who got the data in this region, whether it's Prandtl or whether it's somebody else, Nicorazzi or somebody at Georgia Tech or somebody at Virginia Tech, they are going to get more or less this collapsed graph. Logarithm of Y plus is on the x-axis, U plus is on the y-axis. We have non-dimensionalized the velocity by wall friction velocity. We have non-dimensionalized the distance by multiplying by wall friction velocity U tau and dividing by kinematic viscosity nu. Okay. In the buffer layer, we said viscous stresses plus Reynolds eddy stresses would be the constant together. So when you add it, you're going to get the molecular stresses plus eddy stresses will be constant. If you go towards the viscous shear layer edge, that constant is tau at the wall. Therefore, the sum is equal to tau at the wall. Now we are going to the inertial layer. In the inertial layer, this laminar stress becomes less and less important. The eddy stresses become more and more important. So we're going to neglect this term. That's what Prandtl did. He kept the second term. He still equated it to tau at the wall. So he neglected many, many terms here. Some are neglected because the U and V are 0. There's no pressure gradient. In the boundary layer theory, stream-wise viscous terms are neglected. Even stream-wise eddy viscosity terms are neglected. Molecular diffusion is neglected in the inertial layer. So you're left with just this one term. So you get an expression like this. When you integrate it, it equals tau at the wall. Now, this is a Reynolds stress. So Boosness said a Reynolds stress term can be modeled by density times some eddy viscosity coefficient which need to be found, need to be modeled, times the mean flow velocity gradient equal to tau at the wall. So the bottom line is, how do I find this new t? So this is what we needed to do. So since that time, 1877 when Boosness did, and now it is 1920, people have been developing all kind of turbulence models. Professor Maynard develops some variations of models. Professor Bigger Yang in our school. Other scientists all over the world have been developing models. Although there are some models that are fairly mature, we can use them in our engineering analysis. So Prandtl developed this model. It's now in use 95 years later, not 89 years later. He used a dimensional analysis to come up with a dimensional representation of nu tau. Then he put the relevant physical quantities times some unknown constant. That's how he did it. So in those days, the dimensional analysis was a very powerful tool. So whenever you come across something you cannot model, you first determine what is the dimensions of this. This is meter squared per second. That means it must have units of some velocity times some length. So that's what they did. So Prandtl said the length scale, he said, I'm going to say the length scale is associated with the eddies. This is the boundary layer edge. I'm not going in the outer region, which is called the defect region. I'm not too close to the wall, which is called the Viscous Sub-layer. I am somewhere in between region, called the Inertial layer. Here, the eddies are roughly proportional to the distance from the wall. They cannot be any larger because they will run into the flat plate. So he said the length scale L of the eddies is some unknown constant kappa times y. Okay? So L has got a units of meter or feet. Y has got a units of meter or feet. Kappa has no units. This constant is called von Karman constant because von Karman later on came up and found the constant by curve fitting the test data. Now, how about the velocity scale? Remember, eddy viscosity has got a velocity scale times length scale. So Prandtl said, I'm going to make my velocity scale as the length scale I just found times the mean flow velocity gradient, because there's a length scale here, this length and this length will cancel in units, then I will get a velocity unit. Therefore, the eddy viscosity is length times L times du dy, which is L squared du dy. Notice I put an absolute sign. That's because whether this gradient is positive or negative, the eddy viscosity will always be positive. That's why we put the absolute bar. But in turbulent flow, we know that du dy is not negative. Therefore, in our subsequent slides, we will just call it du dy. Now, we still don't know what this L should be because L is kappa times y. We don't know what this kappa should be. So he said, I'm going to go back to this equation and I'm going to plug in this eddy viscosity that I just model in here and see what happens. So he said, I'm going to plug in nu t, which is L squared times du dy. L is kappa times y, so it's kappa y squared. And then du dy is shown in here, so put it in here. So when you put it in here, you get a rho kappa squared y squared 1 du dy. This is from the eddy viscosity. Then this is the other du dy equal tau at the wall. Now for flat plate, this du dy is a positive number. Therefore, no need to take an absolute value. So you could just say du dy. Here you have tu dy. Therefore, this whole thing is du dy squared. Okay, that's shown up here. Now, we know that the tau at the wall we defined earlier as density times the velocity unit called the friction velocity, u tau. Some books call it u star. We call it u tau. So put the tau wall equal to u tau, rho u tau squared. Rho and rho will cancel out. So you have something squared, you'll have a u tau squared on the right hand side. Take the square root, this will become ky. Square root of it will become du dy. On the right hand side you have u tau squared, square root of it would be u tau. So he said, I'm going to integrate it. I'm going to take this dy to the other side. I'm going to bring this, by the way, I'm going to bring this dy to the other side, y to the other side. U tau is a constant, kappa is a constant, so I'm not going to worry about it. I'm going to integrate the du. So when you integrate the du, you get u. I've taken this kappa to the other side, therefore I have a 1 over kappa. u tau over kappa. dy over y is logarithm of y plus a constant. Okay. dy over y, when you integrate it, you get a logarithm variable. Now, we don't want to do a logarithm of distance quantity. It's kind of a meaningless. Also, we want to non-dimensionalize everything. So what Prandtl did was, I'm going to non-dimensionalize this u velocity by u tau. I'm going to add a logarithm of a constant, which I will take it inside the thing, because log a plus log b is log of ab, that type of a thing. Then the remaining constant will be up here. So he said I'm going to add logarithm of u tau over mu, then subtract logarithm of u tau over mu, then c minus logarithm of u tau over mu is b. Logarithm of u tau over mu and logarithm of y will become this expression here. So this is y plus. So u plus and logarithm of y plus is a linear variation. Kappa and beta are the two constants. So this is a major breakthrough. So Prandtl got this far, but he got stuck. He had no idea how to solve kappa and how to solve beta. So Prandtl was an experimentalist. He's an engineer's engineer. He would go to the wind tunnel, try to take data, come back and stare at this equation. He didn't know what to do. He would come at 6 in the morning, work in the lab. His students will come probably before him, 5 in the morning, work all day, get the data. They didn't know what to do. Von Karman is a thinker. He's not a very industrious. He'll come to the lab around 12 o'clock, like some of our graduate students do, and some of our professors do. He would grab all the data that they got for u and y, test data. Then he will plot u plus versus y plus. So first when he plotted it, it didn't make any sense. So he said, whenever something doesn't make sense, then you plot in a semi-log paper or a log-log paper. So he started plotting the u plus with logarithm of y plus. Then all of a sudden, he got eureka moment. He got a nice linear straight line. He said, why? This is a straight line. U plus as a function of logarithm of y. The slope must be 1 over kappa. So I'm going to find a 1 over kappa. He called modestly kappa the von Karman constant, 0.4. B is the intercept with respect to the y-axis. It worked out to be 5.5. So Prandtl did all the test data, all the hard work getting up to this point. Von Karman got the credit for evaluating this constant and this intercept. Prandtl was floored, very disappointed. He didn't see this. But Von Karman never missed a chance to rub it in. Whenever he wrote a book, he would mention this, how he was so clever. He found the value of kappa and b before Prandtl could do it. So this was a friendly rivalry that lasted a long time. After the Second World War, Prandtl stayed in Germany, but Von Karman came to Caltech, where he made further contributions to our country's aeronautics and also space development. JPL lab, he had a lot to do with it. So Von Karman constant is 0.4 and the B is 5.5. This works for broad range of y plus from 30 to 1,000. So it's a universal relationship. Wherever people collect data for a flat plate, if they non-dimensionalize it, it's going to fit pretty well nicely along this curve fit. So that's the power. Something that was done almost 73 years ago is still holding true because of the way they group these things, organize them together. So we are almost reaching the end of our turbulent flow. So once you have the velocity profile, this has to be curve fitted. It's just a blend of this straight line region with this region. So you curve fit it. Outer flow is, again, there are models available. There are some curve fits available. Once you have the U velocity profile known, you can integrate it and find the momentum thickness, displacement thickness. You can compute the skin friction at the wall, and you can do all kind of stuff. So empirical relations can be extracted. You have used some of these relations, for example, in your very first homework already. And this relationship was shown in a worked out example we talked about in a previous video, worked out example. Now let's do one more numerical example. So these are the new important definitions that we should keep in mind. U is normalized by the friction velocity. Y is normalized by y, becomes y plus by multiplying by density u tau y by mu infinity. Notice that this looks like a Reynolds number. Density times velocity times distance by molecular viscosity. And u tau is the friction velocity. So here is a numerical example. We have seen this before. I'm just going to repeat it. This is a Piper Cherokee wing. It's got almost a 30-foot span, 5-foot chord. So it's flying at 141 miles per hour, sea level. We want to compute the laminar skin friction drag and turbulent skin friction drag. So you have to convert the velocity into meter per second, 63 meter per second. Look up atmospheric density, sea level viscosity. Then you can compute the Reynolds number is roughly 6.93 million. In the laminar flow, CD is 1.328 by square root of Reynolds number. This is the number we get for one side of the flat plate. In your first homework, you derive this. Now, for both sides, here just multiply by 2. 1/2 rho infinity, which is density, V infinity squared, V infinity is given here, CD, which we found here, chord, which is given in here, times span, you get the drag of a Piper Cherokee wing in newtons. To get an idea, what is this 38.4 Newton? Let's say that somebody weighs 160 pounds. They are weighing basically, they are weighing 160 pound mass. They are weighing 75 kilograms. 75 kilograms means because 2.2 kilograms is 2.2 pound mass is 1 kilogram. So 75 kilogram acceleration due to gravity would be 75 times 9.8 would be roughly 750 Newton. So on average, a young person with 150 pounds is exerting a force on the ground of 160 Newton. This is 1/4 of this. So it's like a 40-pound child weight. So that's the drag force if you have a laminar flow flowing over a Piper Cherokee wing. Now let's see what happens if you have a turbulent flow. In a turbulent flow, you have to first integrate the CF. You did this in your homework set number 1. You may remember you got an expression like this. So use this CD instead of this CD. All you have to do is decompute the CD, plug it in. Now you are getting 240 Newton. This is 6 times more than the laminar flow. It's more than somebody would weigh 160 pound person would weigh a lot more than that. Okay. So we have, not a lot more than that. It's a lot more than that. I should have said the laminar flow here, almost 6 times. So turbulent flow is very draggy. Therefore, we try to avoid it. We try to keep a laminar aerofoils, postpone the transition. One of the ways we said is to make the skin as smooth as possible, no roughness. Also avoid adverse pressure gradient as far as possible to remove the inflection point. How thick is the boundary layer? You can use the empirical relationship. 5 delta over x equal to 5 over Reynolds number for the laminar flow. For turbulent flow, delta over x is this number. So if you do the laminar flow, at the trailing edge, the boundary layer thickness is 3.04 millimeter. For the turbulent flow, the trailing edge thickness is 25.4 millimeter. So the turbulent boundary layer tends to be thicker than the laminar boundary layer. So this concludes our brief excursion into turbulent flows. We have now completed all the modules related to viscous flow. We covered it first because this is needed for vehicle performance purposes. So now we are going to go to the outer region, which is the inviscid flow, also called a potential flow.